Hi, I'm Mr. Franklin, and in this video, we're going to talk about Newton's law of gravitation. In a previous video, we talked about what gravity is from a basic standpoint. We did briefly mention Newton's idea of gravity, but we're going to explore his equation more in depth. So this is Newton's equation for gravity. He said the force due to gravity equals mass of the first object times the mass of the second object divided by r squared. Later on, Miles Cavendish came along and he came up with the gravitational constant in order to make the numbers actually come out correctly. So the universal gravitational constant is G. It's 6.67 times 10 to the negative 11th power. And remember, when you have a negative exponent, you're actually dividing by that number. So 10 to the 11th power is dividing into this, which means it's going to be a really tiny number. Okay, so just imagine 0.0000, and there's going to be 10 zeros in front of that 6. Okay, that's how small that number is. Okay, M1 is the mass of the first object, M2 is the mass of the second object, and r squared is the distance between the objects. It's also the distance between their center of mass. So if I have one object here, okay, and at its center, and then I have another object here, we actually calculate that distance from center to center. So it includes the whole distance, okay? That's why we use the letter R. Even though we call it distance, we use the letter R because we are dealing with radius type stuff, okay? And the biggest thing that people will forget when we're doing this is that it is squared. So that's actually going to be pretty important. So that's the basics of the equation. Let's go and let's take a look at the equation at work. So what we're going to do is we're going to take the Earth. So this is an Earth that I created in Blender using NASA imagery and a bowling ball. And we're going to take the distance between them. So the radius of the Earth is approximately 6.371 times 10 to the 6th meters. Basically, it's 6 million meters, not miles, meters, 6 million meters. The mass of the Earth is 5.972 times 10 to the 24th power kilograms. And that's what that number translates to in zeros. And I hope that I got them all because it's a lot. So the Earth is massive, has a ton of mass. And the bowling ball, we're going to pretend that it only has a mass of 1 kilogram. That's actually pretty light for a bowling ball, but we're going to go with it for this example. So the bowling ball is sitting on the surface of the Earth, and so I've drawn it more simply so you can kind of understand. So the bowling ball is sitting on the surface of the Earth, and we look at the radius of the Earth, and now we know the distance between their centers, okay? And we're going to kind of ignore the center of the bowling ball, partly because that would be like not even a third of a meter or a quarter of a meter. So it'd be 637100000.4. Okay, so it's not going to affect our numbers. So we've got these. So I plug them into the equation, okay? And just a note, we are not going to actually be doing these actual calculations in this class. But I want you to understand what the calculations get us, okay? So we plug in G, we plug in the mass of the Earth, we plug in the mass of the bowling ball, and we divide it by the radius, but then we have to square that radius. So only the radius is squared. I have another video that goes through this whole process and review of doing math with your exponents, and what you're gonna find out is it's 10 to the 1, okay? So you got all these big and really small numbers, and the end result is this is the force between them, 9.81 newtons. This is one reason why we tend to skip right to this, because we do a bunch of large math and we get this. What I do want to say is you could plug in your mass of 1 kilogram, the mass of the bowling ball of 1 kilogram, and your distance between them, which would be much smaller. So maybe if you're holding at arm's length, okay, maybe a half a meter, and you could calculate the force due to gravity between you and the bowling ball, because anything that has mass exerts a force due to gravity. It's just because of this constant right here, it's usually so tiny compared to what the Earth does that you don't see it happening. Okay, I mean, you practically have to almost be touching it for gravity to actually, your gravity, the gravity of your body, to actually have any effect on anything. Okay, but when we really are really interested in this are things like planets and stars. Here's what I also want to show you though, is earlier we said the force due to gravity equals mass times acceleration. That's the basic equation for force. And if we plug in our bowling ball of 1 kilogram and our acceleration due to Earth's gravity, little g, guess what? 9.81 newtons. We arrive at the same answer. Okay, so you're going to need to know what happens when we change these, but we're actually not going to do all the calculations with this. If you want to do this calculation, plug it into Desmos, go to desmos.com, click on the scientific calculator, and then just make sure you're using parentheses appropriately. To enter a exponent, just make sure that you, let's say 10 to the 24th. Let's write that. So then I highlight it and then I click A to the B, and now I've got my exponent. Okay, so just be real careful if you're going to use Desmos for any of those calculations, but I love it because it's like a graphing calculator. You can use parentheses and it works. But we're going to do our calculations with F equals ma. The only other planet we are going to go to is not a planet, it is the moon, and we've already done those problems. So let's take a look at the gizmo and see how these forces work. So this is your gizmo that you're going to be working with later this week. You can show the distance between the two, which is 39 meters right now, and I'm going to take it out to 40 meters. We can show the grid so you can actually count squares and all that kind of stuff. We can show the force vector, so which way is gravity pulling? So the gravity of this object is pulling on A this way, and the force due to gravity of A on B is pulling this way. So they're pulling towards each other. So gravity is always an attractive force. Always, always, always. It's always pulling things together, okay? Because if it didn't do that, then we would never stick to the Earth. And we can show vector notation, and the only reason I want you to see this is it actually shows you the magnitude of the force. And the magnitude of the force on A is 0.0417, and the magnitude of the force on B is 0.0417. So the force is the same force between the two objects. So if I get closer, if I bring these two objects closer together, notice that the force gets much larger, okay? We're gonna go over this in more detail in a second. So as I get closer together, the distance underneath the fraction is getting smaller and smaller and smaller. And when you divide by a small number, the result gets bigger. I've done the distance, now let's change the mass. So let's go to 1 kilogram and 1 kilogram. It's actually 1 times 10 to the 5th. Otherwise, we'd have really, really, really tiny decimals, okay? So I change the mass and we get our arrows. So if I double the mass, notice what happens to the force. The force that we originally had winds up being doubled. But notice this, even though the masses are different, notice what happens to the forces. The forces are still the same value, okay? So if I triple that one, it actually multiplies what we had times 3. So let's go back. So 1. So 3 times 1.13 repeating will be 4, okay? So I'm going to triple it, and that's what I get, 0.04. So if I take them further apart, though, notice that the force got smaller. If I bring them closer together, the force gets bigger, smaller. Okay, so that's kind of what we're going to be playing with here some more. So let's go back to the equation and let's take a look at this a little bit better, and I think it'll make some more sense. So here, back to our equation.